So we were in the section or the module, which is numerical differentiation integration. And we had just completed the formula for the second order central difference approximation to the first derivative. And I have an example that I want to do because we're going to use this example when we get to Richardson extrapolation. So the example is f of x is equal to x e to the x. And f prime of x is equal to x plus 1 times e to the x. And f prime at 2 turns out to be 22.16719. Okay. All right. So now if I do the approximation, the central difference approximation, then f prime at 2 is going to be f at 2 plus h minus f at 2 minus h all over 2h. Okay, and so let me draw another quick table. So now this is order h squared. So that means if I divide every time I divide h by 2, I expect my error to go down by 4. Okay, so let's see what we get here. So I have okay, so here's h. Here's the approximation to f prime at 2, and then the error. So when we do 0.1, then I get 22.22879. And then I'm going to divide that by 2. So I'm going to get 0.05. And I get 22.18256. And the error between that approximation is 0.04623. And then I'm going to divide by 2 again. So I get 0.025. And now I get 22.17102. And now you can see my error 0.01154. So it's gone down by approximately 4, which is what we expect. And I'll do 0.0125. And now I get 22.16813. And that is pretty good if you're looking here. And then here. Okay. And now I'm down to 0.00289. Okay, so the second order central difference approximation is wonderful. Now we can improve this. We can always improve by using more points. So the more points that we use, the better our approximation is in terms of our error. So why don't we try one more thing? So let's try an improved. So let's consider now an improved center difference and this is going to have fourth order error. All right, so now we're going to use more neighboring points. And the more points you use, then you can reduce your error. Okay, so now when we did the second order, central difference, we had here, this was our x naught plus h, and x naught minus h. I don't even know if I called it x naught. I think I might have just called it x. Yep, I just called it x. Okay, and so we use those points by doing a Taylor series about x minus h and about x plus h. Okay, so now in order to do my fourth order, central difference, I'm now going to now I'm going to use x plus h, x plus 2h, x minus h, and x minus 2h. So this is a 5-point stencil, okay? So that means I'm going to do Taylor series now about all of those, okay? So I'm going to use, excuse me, f of x plus h let me do f of x plus 2h. So for f of x plus 2h, I'm going to get f at x plus 2 times, plus f prime of x times 2h plus f double prime at x times 2h squared over 2 factorial plus f triple prime of x times 2h cubed over 3 factorial. Trying to think, how far do I need to go out? I can go one more. Plus f, the fourth derivative of x times 2h to the fourth over 4 factorial plus dot, dot, dot. Okay, I need f at x plus h. So that's f at x plus f prime at x times h plus f double prime at x times h squared over 2 factorial plus f triple prime at x times h cubed over 3 factorial plus the fourth derivative of f at x times h to the fourth over 4 factorial plus dot, dot, dot. Okay. Then I need to do f at x minus h. That's f at x minus f prime of x, whoops, too many primes, f prime at x times h plus f double prime at x times negative, oh, nope, times h squared over 2 factorial plus, nope, that one's minus, it's negative, minus f triple prime at x times h cubed over 3 factorial plus f to the 4th derivative at x times h to the 4th over 4 factorial plus dot, dot, dot. Y'all should be good at this by now. And then the last one is f at x minus 2h, which is going to be f at x minus f prime at x times 2h plus f double prime at x times 2h squared over 2 factorial minus f triple prime at x times 2h cubed over 3 factorial plus 4th derivative at x times 2h to the 4th over 4 factorial plus dot, dot, dot. Now here's the thing. I am trying to solve for f prime. Okay, so f prime is what I'm trying to solve for. All right, so this is what I'm going to do. I'm going to multiply the first whole equation by A, the whole second equation by B, the whole third equation by C, and the whole fourth equation by D. Okay? So that's what I have, and that thing continues. And then I'm going to add all this together. So now I need a sum. And the only things I'm going to enforce are the following. I have 4 things I'm trying to solve for, A, B, C, and D. That leaves me 4 degrees of freedom, okay? I really don't want to control anything in the first column, and I don't want to control what happens to f of x. But I do know that I need the sum of everything in the f prime column to equal 1. Then that allows me to let the next 3 derivatives equal 0. And so now I have 4 conditions, 4 unknowns. Okay, so on the left-hand side, I get A times f at x plus 2h plus B times f at x plus h plus C times f at x minus h plus D times f at x minus 2h when I add that together. Okay, so that's the whole left-hand side. Now, on the right-hand side, I'm going to get A plus B plus C plus D times f at x. Okay. The next is the coefficient of f prime of x. So for the f prime of x, I'm going to take f prime of x out, and I'm going to take out an h. And when I do that, oh, and I'm going to take out the 2 over 2 factorial. Let's just take out the 2 factorial. Okay, so what does that leave? Oh, nope, I'm sorry. There is no 2 factorial in this one. I'm a little confused. Let's get rid of that. Okay, so now I see that I'm going to have 2 times A plus B minus C minus 2 times D. Okay, so does everybody see that? So I get 2 times A plus B minus C minus 2 times D. So that is what I get on the coefficient of the F prime. Okay, now for the coefficient of F double prime. So I have F double prime of X over 2 factorial. Its coefficient. So I'm going to have 4. So, and this is times H squared. They're all times H squared. I don't know why it's not erasing. Okay. And when I factor that out, I'm going to have 4 times A plus B plus C plus 4 times D. So I get 4 times A plus B plus C plus 4 times D. And that's the coefficient of the second derivative. The coefficient of the third derivative, and that's over 3 factorial. Okay, so that's going to be, well, I get 8 cubed. So I'm going to get 8A plus B minus C minus 8D. So I get 8A plus B minus C minus 8D. So I think I have one more, which is the coefficient of the fourth. Made 1, 2, yes, the fourth. So the coefficient of the fourth over 4 factorial. So that's going to be 16A plus B plus C plus 16D. And then I have plus something that is order H to the 5th left. Okay, any questions so far? Now I know I need the coefficient of the F prime to be 1. So that says that 2A plus B plus C plus 2D has to equal 1. I'm going to make the coefficient of the second derivative 0. So I get 4A plus B plus C plus 4D is equal to 0. And then the next one is 8A plus B minus C minus 8D is 0. And then the last one is 16A plus B plus C plus 16D is equal to 0. And thank goodness we all know linear algebra. All right, so we can solve this system. And when we solve this system, I get A is equal to Okay, I gotta remember now because my notes are a little awkward. I think, so A and B are switched. Is that right? Let me see. A and B are switched. And then C and D are not. Okay, so I get A turns out to be -1/12. B turns out to be 2/3. C turns out to be -2/3. And D turns out to be +1/12. Okay, so notice that where I have A plus B plus C plus D, that term adds to 0. So the thing in front of the F is going to be 0. So now on the left-hand side, I get well, let's just write what we get. On the left-hand side, we get A minus 1/12 F at X plus 2H plus 2/3 F at X plus H minus 2/3 F at X minus H plus 1/12 F at X minus 2H. And on the right-hand side, the coefficient of the F of X disappears. The coefficient of the F prime is 1. So I just get F prime of X times H. And then the coefficient of everything else is 0. And I just get plus order of H to the 5th. So now if I solve for F prime, I get F prime of X. I'm going to put everything over 12. So I'm going to get F at X minus 2H minus 8 F at X minus H plus 8 times F at X plus H. And then I'm going to get minus F at X plus 2H. I'm going to divide this whole thing. I put it over 12, so I get 12H. And when I divide by H, I get order of H to the 4th. Okay, so that's how you can derive a higher order approximation. Okay. I need to scroll back and see where I am. So 4 was the central difference approximation to F prime. Okay. All right, 5. We want to find an approximation to for the second derivative. Okay. So we're going to do the same thing. This time we're going to use the points, and this is also central difference. Now note, if you do X plus H, and X plus 2H, That'll give you a second order approximation, but it's going to be a forward difference. Okay, so this one's going to be central. Okay. All right, we need f at x plus h and f at x minus h. So I am going to come up here and snatch this and then give y'all a minute to recopy it, because I'm going to snatch that. Okay. All right, so I'll give you all a minute to copy that down. Or at least start the beginning of it. You can always come back to your notes and write it in. Okay. So now I'm trying to solve for the second derivative. So the term I want is this term right here. So clearly, I don't want to subtract. It would be nice if I add those two terms together. So when I add those two terms together, I get f at x plus h plus f at x minus h is equal to 2 times f at x plus, I'm going to just get f double prime at x times h squared. When I add these are going to drop out, just like these dropped out. These are going to drop out. And so now I'm going to get 2, and this should be 4 factorial. So I get 2 over 4 factorial, the fourth derivative of x times h to the fourth, plus other terms. So now I can solve for the second derivative. So I get f double prime at x is going to equal f at x plus minus h minus 2, f at x minus h minus 2f at x plus f at x plus h divided by h squared plus something of order of h squared. So this is a second order approximation. Okay, and it's central. Okay. All right. We can do the same thing. We can find the third order. Any even power, you can always do a central difference, but anything else, it's not going to work. Okay. Oh, not 3. This was, the other one was 5. So this is 6. Error improvement. Okay, so a couple things you can do. One, you can decrease the step size. Obviously, as you decrease the step size, it goes down by whatever the order of the error is. Okay, so your f prime of x is equal to something, some function that you got that's a function of x and h plus your order of h squared, let's say. So if h becomes h over 2, then your error becomes order of h squared over 4. So notice it decreases by 4. And you can do that with something, any order. B, you can use higher order, use a higher order formula that employs more points. And C, which we're going to learn in a minute, is you can use Richardson extrapolation. And here you use 2 derivative estimates to compute a third, more accurate approximation. Okay. All right. Now, all of this is good, wonderful, except what do we do if our distance between our points is not equal? Okay. So the last thing is, what do we do if we have unequally spaced data? Okay, so we can fit. Now, this is actually not what I did in my research. I actually found it, but you can fit a second order Lagrange interpolating polynomial to any 3 points, xi minus 1, xi, and xi plus 1. So if you know those 3 points, then you can fit a polynomial to that. Okay. And then the polynomial can be differentiated to give f prime of x approximated by f of xi minus 1. And then I'm going to have 2x minus xi minus xi plus 1 divided by xi minus 1 minus xi times xi minus 1 minus xi plus 1. So that's the first term. And then the second term is f of xi. And then it is times two x minus xi minus 1 minus xi plus 1. And then this is xi minus xi minus 1 times xi minus xi plus 1. And then you have 1/3 one. And I just don't remember doing this nasty, but f of xi plus 1. And then that is times xi minus 1 minus, oh, I think I'm wrong. Let me make that 2x again. Minus, okay, xi plus 1. Ooh. Nope, xi minus 1. No, something was wrong. Minus xi over xi plus 1 minus xi times xi minus 1 minus xi plus 1 minus xi. Okay. So the disadvantages of this is it is certainly much more complicated. But the advantages, and there are several. You can estimate. So the first one is you can estimate f prime of x for any I interval xi minus 1 to xi plus 1. The second advantage is xi are not equally spaced. So sometimes you're solving a problem and your xi are given to you are not equally spaced, but you still have to try to figure out how to find a derivative. And 3, the estimate is the same as the centered difference if they are equally spaced. So the estimate is the same as centered difference. If they are equally spaced. Okay, so now the last part of this is Richardson extrapolation, and then we'll go on to integrals. And integrals are actually rather easy because you guys have done the trapezoid rule, you've done the Simpsons rule, and so integrals is actually not that difficult. Some of it will be review, some of it will be new, but I think Richardson extrapolation is definitely going to be new to all of you. Okay, so here we want to use, so this is used to generate. So this technique is used, actually, you know what, for a bit, I'm just going to type because it is better if I type this. So, okay. I don't have any variables or anything I'm putting in here. Okay. Oh my goodness, Dawn. What am I trying to do? Here we go. Used to generate results of higher accuracy by using lower order formulas. It's applied when it is known that the approximation technique has an error term with a predictable form that depends on a parameter, usually the step size h. Okay. My hand is giving me a little bit of grief, which is why if I can type, I do. Okay. All right, so here we go. So M is some unknown value. And N of H, this is an approximation of M. So for example, M could be F prime of X. And then N of H could be F at X plus H minus F of X all over H. Okay, so that's an example. Okay. All right, so we already know that M has error. Okay, so M has error. Whenever I take and approximate F prime by F at X plus H minus F at X all over H, I get a bunch of terms, error terms. So M is equal to N1 of H. That's how I'm approximating it, plus what I'm going to call K1 of H plus K2 of H squared plus K3 of H cubed. And then this keeps going on and on and on. But this is really just N1 of H plus order H. Okay. So now that's pretty much like what we have up here. So if F prime is approximated by F at X plus H minus F of X all over H, then that would be my N1 of H, and then my error would be order H, because that is a first order approximation. So now what I want is I want to improve this formula from O of H to 1 of higher degree. So now I have something that is order H. I'd like it to be order H cubed, but I don't want to go back and rederive the whole thing to figure out a new N1. Okay. So what we're going to do is we're going to eliminate the term involving K1. So the first thing we're going to do is eliminate the term involving K1. If I can eliminate the term involving K1, then this thing becomes order H squared. All right, so what I'm going to do is I'm going to replace H by H over 2. Okay, so now I get M is equal to N1 of H over 2 plus K1 times H over 2 plus K2 times H over 2 squared, which will give me H squared over 4, plus K3, which will give me H cubed over 8, plus ... So now M is equal to 2M minus M. So 2M minus M is going to be 2. Now, of course, I'm going to do 2 times the second one minus the first one. So I'm going to get 2N1 of H over 2 minus the first one, which we can't really see anymore. There, I'll try to move it down there. Minus N1 of H plus, I'm now going to get K2, and I'm going to get H squared over 2 minus H squared. Yes, because I multiplied by 2. So this term, yes, that's right. Plus K3 times H cubed over 4 minus H cubed plus ... Okay. So now I have rewritten M in terms of N1 of H over 2 and N1 of H. So now I'm going to let N2 of H be 2N1 of H over 2 minus N1 of H. Okay. So I am taking this piece right here 2n1 h over 2 minus n1 over h, and I am calling that n2. All right, but I'm going to rewrite that as n1 of h over 2 plus n1 of h over 2 minus n1 of h. Minus, minus n1 of h. And I know this looks silly, but I need to divide this by 1. Okay, so now I have n2. Okay, so n2 of h is n1 of h over 2 plus n1 of h over 2 minus n1 of h over 1. Okay, so I am calling that thing n2. And that's n2. Where was n1? Oh, n1 is the first approximation. Okay, so that's n2. Okay. So now m is equal to n2 of h minus k2 of h squared over 2 plus k3 of 3/4 h cubed. Okay, so where did that come from? Back here, back here at this term, that's where I get the minus h over 2. And here is where I get the negative 3/4. Oh, yep, I made a mistake. That should be a negative 3/4. Okay. All right. So now, as you can see, whatever I was approximating m with, I now have a new formula to approximate m with that is now second order. Okay. How did I skip 2? I go from 1 to 3. Where's 2? 1. I have no idea. Okay, well, let's go to 2. That was 1. 2. Now I need to eliminate the term involving K2. So if I can eliminate the term involving K2, then my new approximation will be order h cubed. Okay, so I'm gonna do the same thing now. I'm gonna replace h by h over 2. Okay, so now m is equal to n2 of h over 2 minus k2. So now when I do h over 2 and square it and divide by 2, I get h squared over 8. And then when I do 3 times h, the 3/4 h over 2 cubed, h over 2 cubed becomes h cubed over 8. And then it multiplies by 4 and still a 3. So I get 3 over 32 h cubed plus dot, dot, dot. Okay, so this time I'm going to write, now I'm going to multiply by 4. So I can eliminate the stuff in the first term. So I get 3m is equal to 4m minus m, okay? That is so I can get rid of this 4 in this top term. So that's going to give me, I know this is crazy, guys, but it is crazy. 4n2 of h over 2 minus k2, and then I'm going to get h squared over 2 minus k3 times 3h cubed over 8 minus n2 of h plus, I'm now going to get k2 h squared over 2 plus k3 times 3/4 h cubed plus dot, dot, dot. Now I get 2 terms to cancel. So these 2 terms add to 0. So now I get m is equal to, I'm going to divide by 3. So I'm going to get 4/3 n2 of h over 2 minus 1/3 n2 of h plus k3, I'm going to get 1/4 minus 1/8 h cubed plus dot, dot, dot. And so now I'm going to write n3 of h is going to be this piece here. So this piece is going to be n3 of h. So it is 4/3 n2 of h over 2 minus 1/3 n2 of h. But I'm going to write it in a nice, cool way. I'm going to write it as n3 of h is going to be n2 of h plus n2 of h over 2 minus n2 of h over 3. Okay, so now I have n3. Okay. So now m is now equal to n3 of h plus k3 times h cubed over 8. So now it's of order h cubed. So I can keep doing this. I can now eliminate the term involving K3. And I will get N4 of H will be 8/7 N3 of h over 2 minus 1 over 7 n3 of h. So now I can write n4 of h as n3 of h over 2 plus n3 of h over 2 minus n3 of h over 7. So now you can start to see there is a pattern. So now M is n3 of h plus something of order h to the 4th. Just by starting with one approximation that was order h. So in general, nj of h is going to be nj minus 1 of h over 2 plus nj minus 1 of h over 2 minus nj minus 1 of h all over 2 to the j minus 1 minus 1. And this will give you an approximation of order h to the j. Okay. All righty, that's it for today. We will pick up on Richard's extrapolation. We will finish it on, we will finish this, do an example, and move on to integration. Okay.